Hey guys, this is going to be a video where I do a couple examples using Green's theorem to compute line integrals of planar curves. Okay, so let's just first let's just read this problem. So this first one is going to be an easier problem where we kind of just directly apply the formula, and then after this we're going to do a little tougher one. So compute double integral, line integral here over C of xy dx plus x squared dy. Okay, now C is the boundary of the unit square 0, 1 cross 0, 1 traversed counterclockwise. Okay, that's supposed to be clockwise. Okay, so I'm not going to waste time rewriting that though. So let's just remind ourselves of the formula. So we can take the integral over C of p dx plus q dy and rewrite it as a double integral over d of partial q partial x minus partial p partial y. And then integrate dx dy over d. Okay, so we can write this as a double integral like what we had been doing in chapter 5. Okay. So what is the region here? So d is the unit square. So it's traverse counterclockwise. So you can kind of just think, oh, okay, it's traverse counterclockwise. That should be positively oriented. But just to get some practice, let's just draw it out. So the unit square here, this is like, so this maybe is your y-axis, positive y-axis and positive x-axis. So this is 1, 0, 1, 1, 0, 1, and 0, 0. So this is what it would look like in the xy plane, right? So D is the entire unit square. It's everything in here, this region. Okay, C is the boundary of the unit square. So it's these lines, right, that make up the edges. So this is C. And okay, so now you want to picture yourself walking along this curve. Is the region on your left? Yes. Okay, so this is positively oriented. So we don't have to like multiply by a -1. We just straight up use the formula. So what do we need to use the formula for Green's theorem? We need to identify what P and Q are in this problem and then find their partials and make sure you subtract them in the right order, right? So P is always the function that is multiplied by the dx. Okay, so it's the dx here multiplied by the xy that says, okay, my function P is just xy. And then Q is always the thing being multiplied by the dy here. So x squared is multiplied by the dy, nothing else is. So x squared is my function Q. Okay, so that's how you identify those. Then you just have to find the partials and subtract them. So to get your integrand. Okay, so partial Q, partial Y. Sorry, X. So you always do the opposite one. That is one way to remember it. So the Q is what gets multiplied by the dy, and you always do the opposite one when you take the derivative. Okay, so you want to do partial Q, partial X. Yeah. So, right, this is, of course, just 2x. And then, again, just do the opposite. So P is the function multiplied by the dx. So you take the partial with respect to y. So with respect to y, you just get x. Okay, and now by Green's theorem, the integral that we're trying to compute is the same as if we just integrated over d the function 2x minus x. So make sure you're always taking the q derivative minus the p derivative. Okay, and that's super easy to evaluate, right? D is just a square, okay? So we're integrating over a rectangle. In particular, it's the rectangle 0, 1 cross 0, 1. So this is just integral from 0 to 1, integral from 0 to 1 of, well, 2x minus x, that's just x, dx dy. Okay, so we get integral 0, 1 of 1/2 x squared. X is 0 to x is 1, which of course is just 1/2. And then integral 0 to 1 dy, that's just 1. So we should just get 1/2 here. Okay, so that's our first pretty easy example. Now let's go on to the next one. So now we want to compute integral. Okay, again, these integrals we're computing with Green's theorem are always going to look pretty similar. You're going to have something with a dy, something with a dx over some curve c, right? They're always going to be line integrals. We want to rewrite them as a double integral. It's also possible to use this in the reverse direction where you start with a double integral and then make it into a line integral. But based on the kind of conversation that we had in the video about Green's theorem, well, usually it's a lot easier to just do the double integral than to do the line integral, because line integrals come up, we have to come up with a lot of parameterizations. Yeah, let's actually talk about that for this one. So in this problem, right, let's just first appreciate how easy that was. Okay, we just had to evaluate this integral over a rectangle of x, right, dx dy. Okay, so if you were to actually compute this line integral, you would have to parameterize 3 curves, or right, 3 lines. Right, you have like a C1, right? So they're lines, so they're pretty easy to parameterize, but you'd still have to do 4 of them, right? You have a C1, C2, C3, C4. Okay. And then for each of those, you would have to compute, right, right, f of c of t dotted with c prime of t, right? So it's just going to be a lot of computation if you were to do it as a line integral. So we saved a lot of time using Green's theorem here. Okay, so hopefully that gets you to appreciate this theorem a bit. Okay, same thing here, right? If we were to try and do this line integral without Green's theorem, we'd have to parameterize 2 circles here, which sure isn't that bad. You just use sine and cosine. But you'd have to do 2 integrals. You have to split it up, right? So yeah, this is our curve C on the left here. And first, let's just think about First thing I just want to note here is that the line integral is written a little backwards, right? We have the thing multiplied by dy first, actually. So we're used to it the other way. So this is why I pointed this out earlier. Whatever's multiplied by the dy, that is what you call q. Whatever's multiplied by the dx, that's what you call p. Okay. So our p and q are kind of swapped here. Usually we write the dx first and then the dy, but it's the other order. Okay, so now before I talk about anything else, why don't you pause the video here and decide whether this curve C is positively oriented or negatively oriented. Okay, now that you've unpaused, so first you probably want to just identify what region D we're looking at. And so there are some different regions you can maybe think of this curve enclosing. So the correct one in this case is the donut, right? What's inside here. And this circle in the middle is actually going to make a hole in the region. We don't include that. Because if you were to instead include kind of this whole area, then you would have to also include what is outside of the curve, and that would be, right, an unbounded region. If you think of what's outside the circle of radius 3, right? So this is a circle of radius 3 and radius 1. This is, if you can't see that, just from the picture that I pasted here. The inner circle is radius 1, outer one is radius 3. So this is the region D, it's the donut region, because otherwise we'd have an unbounded region, and we don't want to deal with an unbounded region. So how do we determine if this is positive or negatively oriented? Well, take your computer, throw it on the ground, and walk on your computer screen. No, so you can just visualize it. You could maybe even use your fingers to walk along the computer screen on this, if that helps for you. But if you want to think of like a little guy walking along this curve, and the region D here is on the right, okay? No matter which one you choose, right? If you're walking around the circle of radius 3, it's on your right, and also the one on the inside, right? The region is on your right. Okay, so this is negatively oriented. Okay. Now that we have that, why don't you pause the video again and just try and compute this entire, just do the entire problem, computing that integral. Make sure to use Green's theorem. Yeah, compute this integral on your own, and then unpause when you're done. Okay, now that you have computed the integral on your own, so I believe you should get 40 pi. So if you got that, then maybe you're good, but I'm gonna work out the entire problem here. So we have P and Q, so let's just compute the partial derivatives right away. That's what we're gonna need in order to use the Green's theorem formula. So partial Q, partial X is what we're doing, right? Q is multiplied by the dy, so we take the partial with respect to X. That's just 7. Y squared goes to 0, okay? Partial with respect to X. Little review there. Now partial P with respect to Y. Right, these partial derivatives are never going to go away. Okay, so we have to include this negative here. This negative is part of P, because in the formula we have P dx plus Q dy. Okay, so there's not normally a negative there. We have to include that. So we get negative x squared plus 2y. Derivative with respect to y is plus 2. Okay. So our integral becomes, so the line integral we got by Green's theorem is the double integral over d of, well, q dx is 7 minus p dy, which is 2. Okay, so we're just integrating the function 5. Over d. So there are a couple ways you could do this, right? Since you're just computing the double integral of a constant 5, you can just take 5 and multiply by the area of d. Okay, so maybe you geometrically compute the area of d here just using the area of circles, and then that becomes your, you just multiply by that by 5, and that's your integral. So another way to do this here is to convert to polar, right? So since we have circles in the mix for our region D, why don't we convert this to polar? Theta just goes from 0 to 2 pi, and R Well, we have a hole in the middle. This is a donut. So r goes from, it starts at 1 and goes to 3. And then remember the Jacobian for this transformation. If you're doing the polar coordinate transformation, the Jacobian is r dr d theta. Right? Sorry, the Jacobian is just r. Right? So you have to multiply by r, and then dx dy go to dr d theta. Okay. So this is our integral. We get 5 times, right, this function here is just r, and this is independent of theta. So the integral 0 to 2 pi of d theta, that just multiplies it by 2 pi. And then integrate r dr, that's 1/2 r squared. Okay. So this becomes 10 pi times 9/2 minus 1/2, which is 8/2. In other words, 4. So 4 times 10 pi gives us 40 pi.